So, good morning, everybody. And we are now in the part 2 of the conference, which will primarily deal with model Hamiltonian approaches. So, part A, as you know, right, we essentially dealt with materials, and the standard strategy have been to map this very interacting problem to a problem of single electron moving an effective field. And then you learn how that could be repaired to calculate excited state properties by EW method. Then topological properties would be understood by one-yearization. And yesterday there was a great discussion on wave function-based methods. Well, so there is another approach, which is model Hamiltonian approaches and techniques to solve those model Hamiltonian. And there are many techniques available, and we have to be selective. So we have chosen DMRG, density matrix renormalization group, tensor networks, and also mean field approaches. This is what we have chosen. And we are fortunate that today we have Professor Ramasesha from Indian Institute of Science, Bangalore, right, one of the stalwarts in this field, and he's going to talk about DMRG. And I think the next 4 days will be equally exciting, and I hope you will all enjoy it. So, Professor Ramasesha.
So, thank you very much, Professor Dasgupta. And I'm going to, what's this noise of it?
The people are logging in. Can you just switch off this panel?
Thank you. So, I'm tasked with giving 3 lectures. One lecture is on the general introduction, and 2 others on DMRG. One of them is static DMRG, and the other one is dynamic DMRG. So, I'll just give you the plan of my talk. So, in the first talk, I'm going to be talking about basic approximations, which are common to everything. That's like the Born-Oppenheimer and the independent particle approximations. Then I'll give a very brief introduction to second quantization, and then how to go beyond mean field theory. What are the techniques that are present, like variation and perturbative configuration interactions. Then you have the coupled clusters and the quantum Monte Carlo. And then I'll talk a little bit about model Hamiltonians. I'll introduce you to the concept of model Hamiltonians and what are the symmetries in the model Hamiltonians. And I will briefly touch upon some exact diagonalization methods and their drawbacks. Then in the second talk, I'll talk about the renormalization method in conceptual problems, the DMRG group method, infinite and finite DMRG algorithms, DMRG method and how it is related to matrix product states, and then a little bit about tensor networks and FETs. And then I'll talk about DMRG for excited states, basically because in molecular systems you want to look at excited states, and then frequency dependent properties and time dependent DMRG methods. So this is the plan of the 3 talks that I'm going to give. Well, the first one, I just want to give you a very, very brief introduction to, some people tell you almost anything can be done numerically. You have so powerful computers, why do you need approximations at all? I just want to tell you without approximations how it's impossible to do many things. Okay, let us look at a very simple case of argon atom. Argon atom has 10 electrons. 10 electrons means 30 coordinates. X1, Y1, Z1, X2, Y2, Z2, etc., Xn, Yn, Zn. And then we want to seek ground state at only 10 grid points along each axis. So along x-axis, x1 10, x2 10 points, x3 10 points, y1 10, y2 10, like that. So total number of points at which you need numerical solutions is about 10 to the power 30 points. Okay, let's assume that if each solution takes about 10 to the power 3 floating point operations per second, then with a petaflop machine, which is a 10 to the power machine, time taken is about 10 to the power 18 seconds. 10 to the power 18 seconds is 31.7 billion years. So it will take you 2 billion years to get one of the crudest solutions for the electronic wave function of the argon atom. So it is not possible to do without approximation. So if approximations are a part of life, and without them, you will not. Without them, you won't be able to go anywhere. So in electronic structure calculations, there are two basic approximations. The first one is called the Born-Oppenheimer approximation. So supposing I try to write down the total Hamiltonian, which is the electronic part of the Hamiltonian, which is actually electron repulsion and kinetic energy of electrons, and then the nuclear part, again nuclear repulsion and kinetic energy of nuclei, and then the electron nuclear attraction. So what the Born-Oppenheimer approximation says is that the total wave function, which is a set of depends upon the complete set of electronic variables and the nuclear variables, can be actually written as some parametrically dependent electronic wave function, which is psi r, and r is parametrically dependent, and to show it is parametrically dependent, I have put it as a subscript, and then a nuclear wave function. So if you stick this in, you will get into the total Hamiltonian. Then you will get actually two Hamiltonians that you can write down. One is the electronic Hamiltonian, whose wave function is psi of r at r, and it depends, the energy depends upon the internuclear separations. Okay, and again the wave function. Then the electronic part, actually Hamiltonian depends upon the electronic kinetic energy, electron nuclear potential energy, and the electron repulsion energy. If you look at the nuclear part, then the phi of r, here becomes this wave function for the nuclear part, and you can write down h nuclear phi of r is total energy phi of r. And what is the nuclear potential? This thing Hamiltonian, kinetic energy of the nuclei, then nuclear repulsions, and then you also have the energy of the electronic state, h sigma. So which means the state in which your electrons are present is going to decide what the nuclear vibration state is. So for example, you will not have the same vibrational spectrum if you are looking at the singlet state or the triplet state or the second singlet state.
There was a message which said that the sound is not clear. The message just appeared.
Oh, is it?
Chat works.
This is for your thing.
Not yours.
It's in the internet.
The internet.
Maybe the mic
message.
has to be.
Okay, so
The message on the Zoom.
Just asking whether other people can hear
oh,
No, not these people.
online.
Yeah.
online.
Oh,
There's no problem. 190.
probably you have to increase the volume on that.
Yes.
Okay, you go continue.
Okay, let me continue.
Okay, he says that. Yeah.
So if you look at the neglected terms are basically cross terms which involve the differential of the electronic wave function with respect to nuclear coordinates, and then a mixed differential of the electronic coordinates and the electronic wave function and the nuclear wave function with respect to the nuclear coordinates. If you look at this, if you look at the expectation value of the first term, it goes to 0. So basically, the approximation is pretty good. If you look at the second term, then what happens is that it gives you this energy expectation value is like the mass of the electron divided by the total mass of the nuclear system times the the kinetic energy of the electron. So that's what you will get with this one. So the approximations are pretty good, but there are cases where this approximation does not work. Places where it does not work is, for example, if you are looking at the metal. In metal, thermal resistance, the electrical resistance comes because of the excitation of the electrons when the nuclei move. Okay, that's the electron-phonon interactions that are there. And then you also have what are called dynamic Young-Tunnel distortions in molecular system, molecular complexes, inorganic complexes, molecules. There, if the molecule is vibrating, it keeps changing from one electronic surface to another electronic surface, and that's called the dynamic Young-Tunnel effect. And of course, the electrical resistance, superconductivity, these things come from the electron-phonon interactions. And this Born approximation is very widely used in electronic structure calculation. So you only go beyond that when you really want to look at internal conversions, inter-system crossings, and so forth, which the chemists usually do. Well, what is the independent particle approximation? The independent particle approximation assumes that the electrons move independently of each other, which means the probability of finding an electron at one electron at one point is independent of the probability of finding another electron at another point. So you can actually multiply the two probabilities to get the joint probability of finding the electron one at one point and the electron two at another point. And the many electron wave functions are thus product. But then electrons being fermions, they also have to obey Pauli exclusion principle. So if they have to obey Pauli exclusion principle, then the wave function can only be written as a slated determinant. One of the ways of writing it is this one, where fields are all the spin orbitals. Okay, they contain spin as well. So it is n factorial 1 upon root n factorial is a normalization constant, and this is the slated determinant that you write down for the this independent part of the approximation. So the orbitals can be obtained by minimizing the expectation value of the Hamiltonian with respect to constraint of normalization. That's what we do in the Hartree-Fock calculations. You derive the Hartree-Fock equations that way. Of course, this you have to there's one more step that's involved. It's actually unitary transformation of the orbitals to make the Lagrange parameters become energy functions. Okay, and then another thing that you do when you do the Hartree-Fock calculations in practice is replace the exchange integrals are replaced by empirical potentials to obtain one electron equations, which can be solved self-consistently either to obtain atomic orbitals, or you can also use a linear combination of atomic orbitals to get the molecular orbitals. And actually, this forms the basis for mean field theory, self-consistent field, or Kohn-Sham density function theory. So Kohn-Sham density function theory, as it is implemented, is like Hartree-Fock with empirical potentials, which is actually functionals which are designed to give the best results for given situations. Mean field theory misses many important physical phenomena, both in physics and chemistry. For example, it misses magnetism, it misses Mark-Hubbard metal insulator transitions, and in molecules, you can show that it cannot give you correct dissociation of the hydrogen molecule. The simplest molecule you can think of is a hydrogen molecule. It does not dissociate it correctly. The potential energy surface for dissociation is incorrect. And it also gives wrong ordering of excited states. For example, in the case of nitrogen, the lowest energy excited state is actually not the pi, but the sigma. Okay, so these are some of the problems that are there with this mean field theories, and they have to be fixed. And how does one fix it? Well, before I go into that, I'll just give you a very brief introduction to certain quantization. Before doing that, let me tell you that when I say this thing is slated determinant, I've got all these orbitals which I have written as chi1, chi2, chi-n. They are all occupied orbitals because this is the Fermi energy or the zero of the energy. And these are all bonding orbitals, these are all anti-bonding orbitals. And you can write down the this slated determinant corresponding to this. As you see, chi1, chi2, etc., they are all spatial orbitals. The spin is designated by a bar, which means it's a beta spin. Without a bar, it's an alpha spin. And slated determinants have built-in antisymmetry because you just interchange any two rows or two columns, then the determinant changes sign, and that's equivalent to changing particles. The problem with n by n determinant is an n by n slated determinant has n factorial terms. So actually evaluating matrix elements involving these kinds of slated determinants is rather difficult. Okay, also they have been done in earlier days. So what was done was to introduce the concept of second quantization operators. So what you do is the following: you think of a vacuum state, that is, no electrons are there anywhere there, and then you say if I have a creation operator, AI dagger operating on 0, it puts one electron in the orbital I. Okay, so that's what it has done. I1 is. And then you want to put a second orbital, you put A dagger J in the jth orbital. So which will, it is going to give you, this one gives you chi J2, chi1 minus chi J1, chi I2. Okay, and this part to be antisymmetric, what you should have is, it's very annoying, you know, they're like keeps blinking.
This is what the you can't stop this, right?
Okay, so if you interchange two electrons, the wave function has to change sign. That's equivalent to reversing the order in which you are going to put electrons in the orbitals. So if you put the orbitals as J in first the electron is put in J and second is I, then you'll get a negative sign. Okay, chi I2, chi J1 instead of chi J2, chi I1. Or in other words, you have AJ dagger, AI dagger is equal to minus of AI dagger, AJ dagger, which means AI and AJ should anti-commute. Okay, so this is absolutely essential for something to be this thing fermionic state. Okay, so I'm only going to give you introduction to fermionic creation annihilation operators because that's what we are going to be dealing with. So you have AI dagger AJ dagger plus AI AJ dagger AI dagger is actually equal to 0. And similarly, you can show that because of Pauli exclusion principle, you cannot put two electrons in the same orbital. It means that AI dagger is operating on 0 is 0. And if you take the adjoint of these creation operators, you have the annihilation operators. The annihilation operators is going to remove an electron from an orbital. For example, AI on chi1 removes the electron from orbital chi, and so you are going to be getting a vacuum state back. And you can also show in very simple ways that the annihilation operator is also anti-commute. AIAJ anti-commute, and it follows from the Pauli principle. And then, if I am looking at AI dagger AJ, that is, this is both annihilation operators and this both creation operators. So if I'm looking at anti-commutation of one creation, one annihilation operator, then that is going to be delta IJ. And one can show these things easily. There are many books, okay, from where you can actually get this information. Then you define a number operator Ni, which is AI dagger AI, and the number operator, by the very fact that it is fermions, should have idempotency. That is Ni squared is equal to Ni. So you cannot put more than, so Ni can be either 0 or 1. You cannot put more than one electron into an orbital. Well, if Ni squared is equal to Ni, it means Ni equal to 0 or 1. And that is the Pauli exclusion principle. The important thing is these are basically mathematical constants. See, the commutation relationships that you know involve dynamical variables. For example, momentum, angular momentum, position, energy, and things of that kind. So the first quantization deals with commutation of these operators, actually, which you can get from Poisson brackets. But on the other hand, the reason why it's called second quantization is because these have nothing to do with first quantization operators. These are operators that have been constructed for convenience. And so, this is called the second quantization formula. Okay, let us say how we can represent operators. If you want to represent operators in the second quantization, if I look at a one electron operator in a basis of orbitals chi, then I can actually write H in terms of HKL. HKL are the matrix elements involving these orbitals, and the chi k and Prof chi n. So this is a general form of an operator, because what it does is to scatter a state from a state L to a state K is what it's going to do. So this is the Hamiltonian operator in first quantization notation. Now you know that the system, you can the chi k is done by A dagger K and chi L is by AL. So I can actually write the whole operator in terms of H equal to sigma KL, HKL, A dagger K. So this is, if you also include sigma, the spin, then this can be written in terms of KL sigma, HKL, A dagger K sigma, AL sigma. So this is the second quantization form of the one electron operator. Pretty simple to show. And let us see how you can represent two electron operators. So two electron operators is the integrals involving 1 upon R12 or the two electron operator G between orbitals I, J, K, L can be written as G, I, J, K, L is chi I1, chi J2, G, chi K1, K, L, chi L2. And the second quantization representation of this operator is in this form: G, I, J, K, L, A dagger I, A dagger J, A, L, A, K. So this interchange of symbols, instead of AK, AL, you are writing to AL, AK, simply to eliminate self-interactions. Okay. So when you are deriving it, you will see it very clearly. Or you can also show that if you have just one particle in the system, then if you write it as AK, AL, then the two electron integral does not vanish. So if you have only one particle, you don't have electron-electron repulsion. So then there is going to be wrong. So that's the reason why you write it. And of course, if you have spin orbitals, spatial orbitals, and spin functions, then you can write it in the form of G, I, J, K, L, A dagger I sigma, A dagger J tau, A L tau, A K sigma. So this is the form of the two electron operator that you write. Let us see. Like I said, there are problems with mean field theories. Mean field theory is extremely useful for ground state properties very often. So, for example, if you are looking at material properties in the ground state, then mean field theories and density function theories are extremely useful. But on the other hand, if you want excited state properties and excitation gaps and things like that, then mean field theories are not good. So the techniques that you have are basically configuration interaction methods for going beyond mean field approximation. So you have variation methods, which involve just singly excited configurations, single and double excited configurations, etc. I'll tell you what they are in a while. Then you have the perturbation methods. Most commonly used perturbation method is the Rayleigh-Schrodinger perturbation theory using Euler-Placet formalism, where it's called the many-body perturbation theory or Euler-Placet perturbation theory. There are some problems with variational methods, okay, like size consistency, which I'll talk about, because of which people do coupled cluster methods. And then in the case of Hubbard model, you can do another kind of calculation called the Gutzwiller variation method, which involves only one parameter, and that parameter is the probability of double occupancy. Okay, so we'll talk about some of these. And then you have non-perturbative techniques. The non-perturbative techniques are quantum Monte Carlo methods, and then the density matrix renormalization group and related methods. You also have exact diagonalization methods for model Hamiltonians, but usually good for very small systems. Well, what we mean by configuration interaction methods is the following. That is, the true wave function is actually not just a single determinant wave function, but it also involves wave functions which involve excitation from the pth occupied orbital to the tth empty orbital. So what's on superscript is an empty orbital, what's on subscript is an occupied orbital, and each term like this VPT gives you an excited slated determinant. It's called a singly excited slated determinant because you have removed an electron from one orbital in the occupied space and put it in an orbital in the unoccupied space. And you have many of those these excited configurations. I have only shown one here simply. So, and you have the configuration, the coefficient CTP. You can also have doubly excited configurations, which means you take one electron from orbital T, one electron from orbital Q, put them in orbital T and orbital U. So this is the doubly excited one. Here is a triply excited configurations. So a true wave function is actually a linear combination of all these, and which means that you have determined all these coefficients CTP, CTQ, CTQR, TUV, etc. Okay, these require a variational calculation, which means you have to set up the Hamiltonian or the expectation value of the Hamiltonian, this side true, and then minimize the expectation value with respect to these coefficients. And these are called the single excitations, these are called double excitations, these are called triple excitations, and so on. And it's also possible that instead of using a single reference, that is the ground state, with all the occupied orbitals, you can also have different reference states. Okay, you can have a reference state itself is singly excited. So if you have a singly excited reference state, then and the ground state as another reference state, you call them multi-reference calculations. In this multi-reference calculation, what happens is in the excited reference determinant, you are creating double excitation, which means in actual fact you are creating triple excitation. So this is one way of taking the excited multiply excited configurations without having to go beyond single theta. In the Euler-Placet perturbation theory, the perturbation is actually written as the Hamiltonian is written as F plus A, which is actually the Fock operator, P naught H minus V P naught. So this is the shifted Fock operator that you call. Okay, the H naught is a shifted Fock operator, and then the perturbation V is just given by H minus F and this term. Okay, so the first order correction is actually just zero because of Brillouin theorem. Because if you are doing a Hartree-Fock calculations, then you can show that by the very fact that it is a variation calculation and the first variation is zero, means that if you just change one wave function, then this correction is not going to be affected. Okay, and the second order correction is given by a simple second order perturbation theory, which is given here. Similarly, we have a higher order corrections. The nice thing about this perturbation theory is that it is size consistent in every order. So what do we mean by size consistent? Let me tell you what it means just by writing down a little bit. So if you have one hydrogen molecule and do a CI calculation, okay, then you get energy of one hydrogen molecule E of H2. Now you take a second system, which is H2, the two hydrogen molecules are infinitely separated, and do a CI calculation at the same level. Okay, so let us say that this is singles and doubles CI, these are singles and doubles CI. And you get energy of two hydrogen molecules. In variation calculation, what happens is that the energy of two hydrogen molecules is not equal to twice the energy of one hydrogen molecule. This is in CI SD. This is also CI SD. Okay, and if you look at a book like Stefan Rossler, it will explain to you why this is the case. Okay, so that's one of the problems that you will find. But perturbation theory is size consistent in every order, and that is known as the linked cluster theory. Yeah.
What is the form of the Prof operator you mentioned?
Prof operator is basically a kind of one electron operator. It has the kinetic energy part, or the plus the average potential of the electron-electron interactions plus the one electron potential. So it's what you will get from doing a Hartree-Fock calculation. Okay? So the Hamiltonian that you get from Hartree-Fock calculation is the one electron. So in order to overcome that problem of size consistency, coupled cluster theory came up with a different way of doing it. So it said that the wave function size CC coupled cluster is given by an exponential operator T raised to power T times P naught, where T is actually an excitation operator, which is 1, which gives rise to P naught, T plus T squared upon 2 factorial, T cubed upon 3 factorial, and so forth. So if T is only a single excitation operator, this T gives you single electron hole excitation. The T squared gives you double electron hole excitation. T cubed gives you triple electron hole excitation, so forth. So which means if you have two molecules, then T squared takes care of doing CI, single CI on both the molecules, and so on and so forth. That's the reason why it will be size consistent. T itself is a sum of various different kinds of excitation. T1, T2, T3, etc. So T1 operating on P naught will give me TPT, which is the same as CPT that I had before. PPT, T2 on P naught is going to give me this part, and T2 on P naught is going to give me the same thing, which is two different excitations, that T2 squared. Okay, because it's squared. So there are two excitations which are multiplied. One is TPQ to TU, TRS to T, this thing, UB or BW, whatever. Okay, so that's what you do. And if you are trying to do a coupled cluster singles, it means that you want to do singles, doubles. It is CCD, singles and doubles is CCSTs, and then CCSTT. So basically, one of the things that you will see in quantum chemistry is an alphabet soup. So depending upon the technique you have used, you'll have a, I think the 26 alphabets are not enough, so they are going to put numbers and plus and minus and all that. So it's basically an alphabet soup. And you have to solve the Schrodinger equation, which is H e to the power T P naught is equal to ECC P naught, and this can be solved by standard methods like linear algebraic equations, solvers. And is one of the most accurate methods for obtaining electronic states of small systems in quantum chemistry. It's widely used. Now I come to different kinds of methods. Okay, so The first one were all arbitrary-based methods. Now I am talking about quantum Monte Carlo method. See, the first classical Monte Carlo by Rosenblatt, Teller, and Teller was sometime in the 50s. Okay, and it was based on ergodic Markov chains and so forth. But around 10 years later, Hanscom suggested using a similar technique for quantum systems. So what he did was, you take the Hamiltonian H as H naught plus sigma over I, Hi. You want to find out what an expectation value of an operator F. That is trace F e to the minus beta H divided by trace e to the minus beta H. Okay. So the trace F e to the minus beta H, I can actually write as trace F e to the minus beta H naught e to the minus beta sigma or I Hi. Okay. And H naught is something that is non-interacting, and Hi contains the interacting terms. So this is how you write down the trace, and you want to evaluate this trace because F is going to be given by this trace. What you do is expand e to the minus beta H. So when you expand e to the minus beta H, okay, what you get is minus beta to the power R upon R factorial, and then trace of this product H1, Hi1, Hi2, Har. And you have altogether R factorial terms coming in there. So you will have all these Hi1, Hi2, etc. appearing in different order. Okay. So it may be H1, H2, HR, and the second one will be H2, H1, H3, HR, and so forth. Okay. So they will be slightly in different orders that you are going to get these operators, and you have to evaluate these traces. And because these things don't commute, so you are a bit, you have to be a bit careful. So what you do is you can write down the same expression F as some probability pi gamma R times the quantity that you calculate F gamma R. And F gamma R is nothing but one of the traces. A trace corresponding to one of the sequence of operators having odd operators in the term, and then you are trying to calculate the expectation value of trace F e to the minus beta H naught times one particular sequence of R operators, that is F gamma R. And pi gamma R is a limiting probability, which is of the Markov chain. And how do you simulate this? To simulate this, what you will do is, like I said, F gamma R you can evaluate in this fashion. You define a probability pi gamma R, which is given by something that is proportional, the arbitrary constant A, so that you maintain the total probability should be 1. So this is a kind of normalization constant. Minus beta to the power R, trace e to the minus beta H naught, Hi1 to Har by R factorial. You see that the operator F is not here. So this is the denominator. Okay. So this you have to do, and you have to keep sampling. So now what you have got is you have got a large number of these terms, okay? Because every R term is R factorial terms, and you have infinite number of these terms, okay? Like corresponding to H, the term of power 1, term of power 2, and then term of power R, and so forth. And you have to sample these. So which means either you have to add another operator to the string or remove an operator from the string. So because all these correspond to the states of the Markov chain, so you have to randomly either add or remove, and also you have to make sure that you must be able to calculate these things. And once you calculate these things, you'll know the probability pi gamma R, and you sample these configurations, which are these configurations that I have with the probability pi gamma R using a Monte Carlo scheme and average. So it is something that was introduced sometime in 1959 or something like that, okay? But was never used for a long time. And later on, it was Anders Sandvik who actually resuscitated this method and developed a method which is now known as the stochastic series expansion technique. In the stochastic series expansion technique, instead of having an R which is variable from 1 to some infinity, you will just have a finite number, and then you will pad whenever it is less than the finite number of operators you have chosen. To generate those terms, you will pad with the identity operators and so on and so forth. One of the persons who worked with Anders Sandvik is Arnab Sen from SCS, and he is an expert on these techniques. And if anybody wants to find out more about it, you can talk to him. And of course, Sandvik himself has written a beautiful review in Advances in Physics. And then there are other quantum Monte Carlo methods. So this was one of the earliest quantum Monte Carlo methods. The other quantum Monte Carlo methods use what's called the Prof decomposition. In the Prof decomposition, you take e to the minus beta h and write it as limit L tends to infinity e to the minus delta tau h raised to power L. Delta tau is beta by h. Of course, you can't do that because h has got non-commuting parts. But nonetheless, in the limit L tending to infinity, this is an exact expression. So instead of doing this L tending to infinity for your convenience, you take some finite value of L. Once you take finite value of L, you only have a finite number of terms. You can introduce complete sets of states between operators. Okay, and then you will get a whole series of matrix elements, and then you will have a beta axis or imaginary time axis, as you call it, in which you can go from one kind of term to another kind of term. So it is written, it's what's called, it's written as a checkerboard pattern for bipartite axes, and you can sample them using techniques like the Monte Carlo technique, but they are not the most efficient ones because you get into what are called the ergodicity problems in Monte Carlo, where you will not be able to, you will get stuck with a certain configuration and you can't easily change it. So, but this is just, I'm just giving you a flavor of what quantum Monte Carlo methods are. And the other one, quantum Monte Carlo method, is what's called the auxiliary field Monte Carlo method. So this uses basically a Hubbard-Stafford transformation. It is based on the functional integral techniques. So what you have is the interaction part, if it is e to the power a squared by 2, is actually written as an integral over some auxiliary field S times a linear term A. So this is actually e a squared by 2 is written as root 2 pi integral ds e to the minus s squared by 2 minus scm. And this is a Gaussian integral which is easy to evaluate. For people who did molecular calculations would have actually used Gaussians and these kinds of Gaussian integrals. So it's easy to evaluate. Once you do that, it can be shown that for fermions, the auxiliary field need not be continuous. So S is not continuous, it can only take two values, plus 1 or minus 1 fermions. So it is not an integration, it's just a summation. And for every interacting term, S A, you will have two auxiliary variables. One auxiliary variable which can take two values plus or minus. So if you have n interacting terms, you will have n auxiliary variables. And the Hubbard-Stafford transformation leads to an ensemble of non-interacting terms, because what you have is a squared here, which is an interacting term, because a is the electron. This is a number operator or operator which corresponds to one electron term diagonally j, and then a squared corresponds to two electron terms. And here you see that it is dependent linearly on a, and e to the minus s squared by 2, and this integration can be replaced with summation with s equal to plus 1 or minus 1. So if you have only one interacting term, then you only have just one summation of spin variables plus 1 or minus 1, because it's a classical spin spectrum. Well, when you have a Hubbard term like n up, n down, because when an orbital is doubly occupied, there is electron repulsion, two electrons in the same orbital. And that's the first thing that you will always consider. So when you have that, you can write it in the form half of n up plus n down squared minus 1 half of n up plus n down. So this is like the a squared term, and this is just the a term. So you can make a Hubbard-Stafford transformation for this one, and you can compute a partition function involving traces over fermions. So you have to, there are two traces you have to take. There is integration over the fermion variable, and then integration over the auxiliary field variables, which is now in this case not an integration but actually a summation, because you only have each auxiliary variable only has two values, and corresponding to every interaction term you have one auxiliary variable. And to evaluate the fermion trace, what one uses is what are called coherent states. Coherent states are nothing but eigenstates of the annihilation operator. The reason why you do that is the eigenvalues corresponding to the eigenvalue of the annihilation operator, these eigenvalues are not numbers. They are what are called Grassmann variables, which means they are some kind of numbers which anti-commute. Because of that, the exponential operator can only have a constant term and a linear term, nothing beyond that. Okay, anything beyond that will be zero. So when it's only constant and linear term, it's easy to integrate and you get a determinant over there. For integration of the fermion variables will give you a determinant. So this is also known as the determinant Monte Carlo method. And one can do the auxiliary field summation. You can do using a Monte Carlo technique, which is by importance sampling from a Markov. So it's rather simple to do it. So people would do these kinds of calculations for Hubbard models and UV models and things of that kind. Then you have other kinds of quantum Monte Carlo techniques known as the projector quantum Monte Carlo technique. So this is just based on the fact that you can treat e to the minus beta h as a projector. Okay, so you just take out the ground state energy from there, e to the minus beta h minus E0, because you are going to choose a zero of energy to be the energy of the ground state. Then you will see that in the limit beta tending to zero to infinity, everything cancels except that of the ground state, because it is this I can write as e to the minus beta E naught minus beta E1 minus beta E2 etc etc. E naught is zero, so it's just E naught is one. Rather E naught is zero, so that will give you a term which is one, and all the others will give you exponential terms, and as beta increases, the exponential terms go to zero, and what you will get is the ground state. So this is the projector quantum Monte Carlo technique, and even this one, people use the same Trotter decomposition to deal with e to the minus beta h, and then you estimate the expectation value of e to the minus beta. This is the Hamiltonian between side, and this can give rise to a projector-based quantum Monte Carlo technique, which is very similar to the auxiliary field quantum Monte Carlo technique. You can get a ground state energy. Then you also have other methods like the diffusion quantum Monte Carlo methods. So in the diffusion quantum Monte Carlo methods, what you do is from every point in space, you start a random walker, and the random walker can either create more walkers depending upon the potential, or can annihilate itself, and then the number of walkers that end up at the space at the after considerable walk, which is nothing but Monte Carlo sampling. When it reaches that point, then you just find out how many walkers are there at every position, and that gives you the wave function. And this has been used. Diffusion Monte Carlo is very extensively used in quantum chemistry, and the person who actually did a lot of work, the person who had pioneering work in this area is separately. So if anybody is interested, they can look at separately as well. And then you have the variation quantum Monte Carlo technique. So this again, for model Hamiltonians. So you can start with the Hubble orbitals as later determinant, and then you keep changing the occupancy of the Hubble states using a Monte Carlo algorithm. And you also can do a variation quantum Monte Carlo using the Gutzwiller variation. That means what you can do is you can write down your Hubble determinant as one that corresponds to all singly occupied sites, and then one doubly occupied and one empty site, which I call D1 state, D1 site, D2 site, D3 site, and all that. And then you can have a parameter like eta, which varies between 0 and 1, and you can choose your wave function to be either the ground state plus eta times singly doubly occupied plus eta squared times two doubly occupied sites, and so forth. And consider the expectation value varied with respect to eta, and then you can get the energy of the ground state. This was actually used to first predict, by Bickman and Rice, to show that the Hubbard model has a metal insulated transition, because there's a critical U above which you don't have any doubly occupied sites, and it is insulating, and below which you can have doubly occupied sites, so it can be conducting. But this has got other problems, because if you look at this thing, just perturbation theory, even at very large U, you will have doubly occupied, triply occupied, and so on, such states. That's how you can actually get the Heisenberg antiferromagnet. So these are all some of the quantum Monte Carlo techniques that I just wanted to mention to give you a kind of brief idea. But there is one generic problem with quantum Monte Carlo, which is called the Fermion sign problem. That means the probability that you are going to, the way you define your probability, it is not guaranteed that the probability is going to be positive always. For example, in the determinantal Monte Carlo, the determinant may actually go to some negative value, in which case your probability becomes negative. Then how do you deal? So then you have to resort to approximations which are completely uncontrolled, like either throwing out those configurations or by taking the modulus of the probability and so on and so forth. Okay, so this is one of the problems with the generic problem with quantum Monte Carlo method. And also if you have spin systems in which you have frustrated interactions, okay, frustrated spin systems. Again, you have the problem with quantum Monte Carlo with the sign problem. Okay, so how to deal with sign problem is one of the major points of discussion in quantum Monte Carlo. Okay, now let me go to a little bit about modern Hamiltonian. Okay, when you write down your electronic Hamiltonian, you have the one electron part and the two electron. Okay, and the one electron part is just the matrix element Hij is just that of the one electron operator, and IJKL is the matrix element of the two electron operator. What one does in mean field theory is replace the one electron H by H tilde, which is actually self-consistently obtained one electron matrix. Okay, and you can have H tilde KL replaced by some phenomenological parameters like the transfer integral, as in the energy band theory of single band tight binding model and so forth. Okay, so you can do that. Like I said, mean field approach is inadequate to describe excited states, and I also discussed employing configuration fractions and perturbative approaches and so forth. Now let me go there. This is the next slide. Okay. The electron-electron interaction part is this one. Okay, and it is much more convenient to use instead of the physicist notation for IJKL, which is on this side you have the electron 1 and 2, and on this side you have electron 1 and 2 again. So Ij are the bra vectors and Kl are the Ket vectors. Instead of that, you write down what is called the overlap charge cloud representation of the two electron integrals, which is represented as IJKL. Electron 1 sits in the orbitals I and J. Okay, the electron 2 sits in the orbitals K and L. So the overlap cloud of orbitals I and J is electron 1. Overlap cloud of orbitals K and L, electron 2 is sitting, and you have with this operator now becomes Eij minus delta Jk Eij. Sorry, there must have been Eij Ekl minus delta Jk Eij. So there are two of these operators. Please make sure there's a correction. Eij Ekl minus delta Jk Eij. I made a mistake. So let us look at the two electron integrals. The two electron integrals involve electron 1 sitting in the overlap cloud of Pi star and Pj. So these are the Gaussian orbitals I've just shown, and these are different sides I and J. And the electron 2 is on sides K and L, Pk star Pl. So you have the two electron integral IJKL is Pi star 1, Pj 1, E squared upon R1 2, Pk star 2, Pl 2. You see that the overlap of these is going to be very, very big, because the two are kind of Gaussian functions. We are looking at 1A orbitals, then obviously the overlap is 0. Okay, so the two are far apart, and so if the overlap is very small, or the differential overlap, what I call, because it's the integrand, how much it is overlapping is what we are looking at. If that is small, then you can actually approximate this integral by IJKL as IJKL delta Ij delta K. So this is what is known in chemistry as zero differential overlap approximation, because the differential overlap is the overlap of these two orbitals. Okay, or the overlap of these two orbitals. Okay, in the Hubbard model, what you do is, after making the zero differential overlap, you also cut down the range of electron-electron repulsions. So you say that electron-electron repulsions are zero unless the two electrons are sitting on the same orbital or on the same side. So I can write it as Iijj as Iijj delta Ij, and I call it Qi. And the Hubbard model is written in this fashion. Introduced first in 1964, and one doesn't know whether it was Hubbard or Gutzwiller or Kanamori who was the one who introduced it. They were all together, but the name Hubbard is stuck to the model. And is good for metals because screening lengths and metals, deviable screening lengths in metals are very short. And so you can say that the electron-electron repulsions are completely truncated to just on-site repulsions. Then you have the half-filled band. If I'm working with a half-filled band and a very large U by T, then it's quite easy to show using perturbation theory that this gives rise to a antiferromagnetic Heisenberg model. And this antiferromagnetic exchange is what's called Anderson kinetic exchange. Okay. So, and there was the first model of antiferromagnetic exchange. Before that, people only knew how to get ferromagnetism because the direct exchange repulsion between two electrons is always possible, is always ferromagnetic, and so they knew how the ferromagnetic interaction came about, but they never knew how the antiferromagnetic interaction came about. But if the range of electron-electron repulsion is extended to the nearest neighbor, because if you are looking at semiconductors, it's not good enough to actually stop it just on site because they form what are called excitons, and to form excitons, the electron hole bound phase, then you must be able to have interactions between sides. And a model called the UV model was introduced, and this model can also be extended to more than one orbital per site, or it's called a multi-band Hubbard model. Possible to do that. Let me come to another model, which is where you don't make any approximation with respect to the range of electron-electron repulsions, except the zero differential overlap of orbitals. Make a zero differential overlap approximation. You assume that electron-electron repulsions are infinite. Then you get the Hubbard model, the Maxwell-Park model, and Z is actually the local chemical potential. So if Ni is equal to Zi, then the orbital is filled to capacity in chemical systems. So that's what the chemical potential is. And Vij itself is parameterized by various kinds of parameters, parameterization, so that you reduce the model to a single parameter model. Otherwise, what happens is if every V is a parameter, you don't know where to stop. So you always kind of extrapolate between U on on-site repulsion and 0 on or E squared upon R for very large R. And when you do that, then you get one of these approximations, and it makes PPP model a one parameter model. And interestingly, PPP model was introduced in 1953. So to look at it, Hubbard model should be called the truncated PPP model, not vice versa. PPP model should not be called the extended Hubbard model. Because if you look at the precedents, the PPP model came before. Now, for doing calculations, I still have about 20 minutes. For doing calculations,
So if you keep time, about 5 minutes for discussion, so then.
yeah, and I'm also around.
Yeah.
And they can also ask questions.
Yeah.
So please feel free to ask. Well, if you look at an orbital, a Fock space is one that considers all possible occupations of a particular sign. For fermions, if you have one orbital, it can be unoccupied, occupied with up electron, occupied with the down electron, or doubly occupied. And it's 4 dimensional. Okay, if you have a spin half, then it's only up or down. Okay. In case of bosons, of course, you can have 0, 1, 2, etc., whatever it is. But if you restrict to what are called hard port bosons, then you can have 0 or 1. Looks very much nice. So Fock space of a full system is nothing but d raised to the power n. So if you have n sites and each site has a Fock space dimensionality d, the total dimensionality is d raised to the power n. What is Hilbert space? Hilbert space is obtained by specializing the Fock space to a given number of particles. If you want a given total spin, and if you further want a given z component of it. So if you do that, definite number of particles, definite total spin, definite z component of total spin, then you actually specialize this Hilbert space, and you can even have a spatial symmetry the system has, or if there's symmetries like electron hole symmetry, then you can have a point group. Look at the representations of the point groups, and you can have functions transforming as representations of the point groups, and they form the Hilbert system. And most of the Hamiltonians, particularly the Hubbard model and also the isotropic spin-half model, where you don't have any anisotropic interactions or any relativistic interactions, they conserve total spin, which means h comma s squared is 0. And of course, if it conserves total spin, it also conserves z component of total spin. And in bipartite systems, you have electron hole symmetry at half phase. So bipartite systems in quantum chemistry literature are known as alternate head particles. Okay, where you can completely break up your system into two sublattices, and the hopping of the electron happens only from a site in one sublattice to a site in another sublattice. There is never a hopping term which connects sites in the same sublattice. So this is what's called an alternate system, and you can have an alternate system. Then you have the electron hole symmetry that can be actually written as h comma j equal to 0, and electron hole symmetry operator is actually a site operator. Okay, so you can find a direct product of this one to get the electron hole symmetry operator for the whole system, and j operating upon upspin gives you upspin back and minus 1 to the power eta I. Similarly, downspin is minus 1 to the power eta I 0. Operating upon a empty site will give you a W occupied site, and operating on a W occupied site will give you an empty site. Eta I is of course 0 when you have one type of sublattice atoms, and eta I is equal to 1 when you have another type of sublattice. Okay, it's quite simple to show by using these things that the Hamiltonian at half filling is in. And also you have spin inverse symmetry, which means that this is a poor man's way of actually taking into account spin conservation. So what happens is when ms is equal to 0, if you flip the spins up to down and down to up, then the Hamiltonian remains in range. Okay, so this is called the spin inverse symmetry. Yeah.
I think Ji is a vector, right? Three component vector. Your Ji.
No. This Ji is for the site. I is for the site.
No, I mean I'm talking about the capital J.
No, it's actually an operator. It's a 4x4 matrix. The electron hole symmetry operator is not a vector, it's an operator. It's a 4x4 matrix, and the matrix elements are basically given by this quantity. Okay, Ji operating. So up is going to give me minus 1 to the power eta I, and up down will give me this is 0. Down up will give me 0, and down will give me minus 1, and these two will be off at operating on 0 will give me W occupied. W occupied will give me 0. So the J are actually electron hole symmetry operators, and because they are operators, they are main matrices.
So I thought that you were talking about eta pairing operators considered by Chen Ni Yang.
No, not.
But maybe
So,
we can discuss.
But this is something that has been used in both in quantum chemistry and physics literature for almost 40 years.
Thank you.
Okay.
What has to do with superconductivity and negativity?
Oh, okay. I'm not aware of it. Okay, so what the electron hole symmetry does is to divide this Hilbert space with n equal to n into what is called a covalent space and an ionic space. A covalent space is one that has got, in addition to ionic diagrams, it's got all the covalent states. That all sites singly occupied is also included in the Hilbert space. Whereas in the ionic space, singly occupied sites are not included in the Hilbert space. You must have at least one W occupied site. So it's one W occupied, two W occupied, etc. From here, it is 0 double occupancy, 1 double occupancy, 2 double occupancy, etc. And the reason why it's important is because the lowest energy optical excitation is from the lowest energy state, the covalent space, to the lowest energy state, the ionic space. So you can get an optical gap by doing a calculation involving the connection between covalent and the ionic spaces. And if you have, this is wrong, I should not have had H nu. So you have spin inversion symmetry, you have ms equal to 0. It goes into p plus and p minus spaces. And the p plus space will be a space of even total spin, like singlets, quintets, like that, s equal to 0, 2, 4, etc. Whereas this one will correspond to s is equal to 1, 3, 5. So it basically disperses, the ground state into the singlet space, and then the triplet space, which is a spin excited state. They are in different spaces. So the lowest energy state here and the lowest energy state here, the difference in energies will be the triplet gap. So this is also important. So one has to, when you do an exact diagonalization calculation, you have to choose what basis you are putting. So if you are going to use a basis which conserves total spin, then you will use valence bond states. If you want to conserve only total C component of the total spin, you use later determinant basis. And just the spin inversion symmetry you are going to use instead of any of these symmetries, then you will have even or odd total spin is what you are going to get. And exploiting electron hole symmetry, you can have a covalent space and an ionic space. Spatial symmetry, if you exploit, you will have all the different spatial irreducible representations. And within BB basis, we have shown that it is possible to exploit all the symmetries, including symmetries of non-abelian bindings. Well, I'll just give you an idea about what a valence bond basis is. It's very, very simple. Valence bond basis constructs singlets between pairs of two electrons or pairs of two spin-offs. So I'm only going to deal with a spin-off system, and I'm, for convenience, taking it 2n side system. Okay. So what you do is you arrange these 2n spins at the vertices of a regular 2n gauge. Okay. So if it is 4 spins at the space, your vertices of the space, you put the sides. If it is 6, take a regular hexagon, and so on and so forth. And then draw a straight line between vertices that are singlet pair. Okay. If 1 and 2 is singlet pair, draw a straight line between sides 1 and 2. 3 and 4 is singlet pair, draw a straight line between 3 and 4, and so forth. And there is what's called a rumor falling rule. It says you retain only diagrams with no crossing lines. See, because if 1 and 3 are paired and 2 and 4 are paired, then you are going to have a crossing line, two crossing lines in the diagram. Throw it out. But you just take 1 and 2 paired, 3 and 4 paired, or 1 and 4 paired and 2 and 3 paired. So these are the ones without crossing lines, and they will be completely linearly independent, and important is they will also be complete. The point is that they are not orthogonal. They will have a overlap which is non-zero, okay, but they are linearly. So you don't count more states than is required. So I have shown you here what we mean by a line 1 and 2. If the singlet pair, it is alpha 1 beta 2 minus beta 1 alpha 2. If it is electrons, then you can write down creation operators and show it the same way. And if they are W occupied side, then you just say, by a cross, which is at the same side, you have both alpha and beta spins. And if you have parallel electrons at different sides, then you just write it as an arrow involving sides I1, I2, IN, which will be just alpha, alpha, alpha operating on 0, and that will give you the spin n by 2. Okay, because you have n sides. So So like I said, what are legal and illegal diagrams? If this is a legal diagram, no crossing lines, 1, 2, 3, 4, and there is no crossing lines legal, but this is illegal. And illegal diagram can be written as a linear combination of legal diagram. That's why it's called. Nothing, it is not broken any law. And this you can extend to, sites with arbitrary total spin, okay, sites with a higher, not just singlet, but higher spin states, and spin half objects, and so on and so forth. You can do that. For example, I'll show you that here I have a case where I have a spin one side here, a spin one side here, a spin 3 by 2 here, and spin 3 by 2 here. So spin 1 means there are 2 spin half things which are always parallel, and spin 3 by 2 means 3 spin halves which are always parallel. So you can never have a straight line, a singlet line between these 2 sides which are virtual sides. No singlet lines involved, these 3 sides. And so you can write down, pairing of the this auxiliary spin halves, and you can get a valence bond diagram. And for every auxiliary spin, you can associate 1 bit. Okay, and that bit, if it is 1, the spin is up. If it is 0, the spin is down. So here I have shown you that this is 1, this is 0. So there is a straight line, a singlet line between this and this, singlet line between these 2, so forth. And because it's a binary, you can just read out the integer. The integer happens to be 806. If it is a triplet I take, it's a 888. And because of this, you can represent valence bond diagrams by integers. So it's very simple. So all you need to do is look at the bit pattern of the integers using the machine bit testing routines, and you will know whether a particular integer corresponds to the basis state of a chosen total spin. Once you do that, it's easy to generate, it's easy to manipulate, because anytime a Hamiltonian of this is one of the parts of the Hamiltonian operator diagram, what happens is it's just going to reconnect these lines, okay, because it's going to be just flipping some bits. So 1 becomes 0, 0 becomes 1, and so forth. Okay, so that's quite simple to do. And typically, you can reduce the dimensionality of the full Hilbert space. So I have calculated the full Hilbert space dimensionalities. Very simple to calculate using Weyl dimensional formula. You can actually derive it also. The derivative of this formula is also very simple. So here I have for 8, 12, 16, and 20. Singlet states are, here I have 5 billion. Triplet states are 12 billion here. But if I look at S is equal to 0, in the spin case, we have 6 billion singlets. S is equal to 1. In the case of valence bond diagrams, you have 17 or 18 billion triplets. Okay. I think we have been able to do calculations on a 20-side problem, which is using a 5 billion, roughly 6 billion valence bond states, and using symmetry, we can get the exact energies of Hubbard or the Panzer-Markov Hamiltonian. For the spin, you can do probably 36 at 4. So this is quite doable. The advantage is, even though the dimensions are very large, the Hamiltonians are very, very sparse. Okay, because in every, you want me to stop now? Or
5 minutes.
5 minutes. So Hamiltonian matrices are very sparse. For example, the number of non-zero elements in a row is equal to the number of terms in the Hamiltonian. So even if your row is 6 billion, the number of terms in the Hamiltonian is only for 20 or 30. So you only have 20 or 30 terms in this row. You can use sparse matrix techniques, which means throw out all the zeros and do arithmetic only with non-zeros. Easy to calculate static properties. We can toggle with VB and stated determinant states for computing matrix elements. You can do time dependent as well as frequency dependent properties. You can calculate exactly using this technique. Okay, these are the last slide. So, well, given that you can only do a calculation for 40 sites or 20 sites, why is it that the exact calculations are so important? The reason is, if you, for example, in the case of polyacetylene, okay, you can do the calculations for 10 unit cells, which means that you can actually extrapolate. If the correlation length is short, you can extrapolate most of the properties to thermodynamic limit. And if you use open and cyclic boundary conditions, it can give you kind of an error bar for these calculations. It's good to predict critical points in frustrated J1, J2 spin-off chains. It can be used as a check against approximate methods. So if you want to know you are doing DMRT and you want to see whether you have made a mistake in DMRT or not, then you can actually do these calculations and check. Of course, you can also do a non-interactive calculation with the DMRT and check. And like I already said, these are about the largest system sizes you can do. So, but with lattices with large unit cells like polyparaffin finally, you got 8 orbitals per unit cell. You can only do about 2 orbital calculations. Two unit cell calculations is not enough to extrapolate anything. So it's not good enough. And if you have a large 5 coherence lengths, then also it's not useful. And extrapolation methods are basically physically motivated. There is no theoretical basis. So anyway, I just wanted to give you an introduction to various techniques, model Hamiltonians, and so forth. So the next 2 talks will be on density matrix renormalization. Thank you very much for your attention.
Thank you very much, Mr. Ramasesha, for the overview of the field, boundary coordinate system, how to numerically handle it. So, guess some questions from the students. Yes, please.
Nice stuff. So for the quantum Monte Carlo parts, we mentioned that if there is a negative in the determinant, then the process, the entire calculation can be wrong. But
Not the entire calculation. It can give rise to errors.
yeah, okay. So, but when we calculate the determinant and when we use the probability density to generate points in the sample space, we usually take shy star, like, right? So any negative value or anything like that should go away.
Yes, but that is what you are saying is correct. But here what happens is that supposing you are looking at the world lines, then without going through an interaction, 2 world lines interchange. When the 2 world lines interchange, the sign changes. So the technique itself has a problem. It's not the physics, the technique.
Yeah, the technique is a problem, and we know that there is a sign problem when we calculate expectation values. But is it because
even when you calculate probabilities for going from one-step transition probabilities for going from one configuration to another, then also you.
And can you say, like, sign problems, why do they arise in, what is the reason for that?
Like I said, the reason for that is supposing you are looking at world line of particles, okay? So where you have got one fermion world line going this way and another fermion line going this way. So if the 2 fermions on the 2 lines have to interchange, there must be an interaction. Okay, if you have a 3-dimensional lattice, there's a 2-dimensional lattice and with world lines going through, then what happens is that the 2 can interchange without going through an interaction. So when they interchange without going through an interaction, then the term becomes negative. So the matrix element is negative. The previous matrix element was positive. The ratio is going to be. Okay, so that's it. So this one way it can appear.
Okay, thank you.
Any other question? Yeah.
I have a question about the PPP model. So in that model, you introduce local chemical potential Z sub I, right?
Yeah.
But I wonder why we need to introduce that one.
So it comes completely from chemistry arguments. Okay, so supposing I have got carbon and nitrogen in the system. If nitrogen, the one orbital is being contributed by both nitrogen and carbon. Okay, so carbon atom is neutral when there is only 1 electron in the orbital, whereas the nitrogen is neutral only when there are 2 electrons in the orbital. So you are just shifting the energies so that the atomic configurations will correspond to 0. Okay, so that's why you use local chemical potentials. Okay, so a nitrogen atom with 2 electrons is neutral. A carbon atom with 1 electron is neutral. So if they are neutral, not charged, then they don't interact. There's no Coulomb interaction between the two. So if you want to have a Coulomb interaction, carbon atom should be charged, which means either it must have 0 electrons or 2 electrons in the orbital. And nitrogen atom should also be charged, which means it should have less than 2 electrons. Okay. So in order to make sure that the chemistry is correct, we introduce local potentials.
I mean, they are basically fixed
They are
The
fixed,
outside.
yes, they are fixed based on the chemistry.
before the calculation, right? You don't have
Yeah.
to determine them.
No.
consistently.
Okay.
I'm not going, that is why I call them local chemical potentials. I'm not going to change the number of electrons in the system. Number of electrons in the system is a given. Okay, so there's no chemical potential associated. Look, it's a canonical ensemble calculation. you are looking.
Thank you.
Any other questions?
Yeah.
So I had a confusion. When we were speaking about the coupled cluster theory, and you basically the exponential part you're breaking it in the exponential part. The t's are there, and then you have the where the t square suppose is for the double excitation, and then again when you're breaking t in terms of t1, t2, there also I have the double excitation.
Right. Yeah, so I'll tell you why. So now look at the hydrogen molecule problem. I'll tell you why you should have. Okay, if I have a single hydrogen molecule, okay, and I do a SDCI calculation, then the wave function will be H2 or HH, both of them not excited, and then plus HH singly excited, right? Which is one of the states is excited, and then I can have both the H star H star, both hydrogen atoms excited. So this is 0 excitation, this is single excitation, this is double excitation. Okay, if I do the calculation at the same level for 2 hydrogen molecules, so I will have HH0, okay, and then I can have H star H, HH, or HH star, HH, and so forth, okay? So you can have an excitation here or there. Then if I have double excitations, then I'll have the following. Okay, I can have both the excitations on the same molecule like here, or one excitation on one molecule, another excitation on the other, and so forth. Okay, but if you want to get twice this energy, you also should have these excitations, right? One of them is singly excited, and the other one is doubly excited. Okay, or you must also have the configurations like this. Both the hydrogen molecules doubly excited. Okay, because these are left out when you do a single CI, when you do a single double CI, variationally for 2 hydrogen molecules. Okay, but what coupled cluster theory does is actually takes a T square, okay, T2 square. So what T2 square does is it does a double excitation of one molecule, and it also does a double excitation of the other molecule. So it will take both of them into consideration. Okay, and T1, T2 will consider this single excitation molecule 1, double excitation molecule 2. Okay, so that when you square it, okay, you get the correct wave function, and you will have the size consistency. So if you want to get size consistency, then it is necessary that the same excitation has to be, applied on different parts of the system. If you don't do that, you don't decide. Okay. Does it answer your question?
Yeah, fine.
Okay, so if there are no more questions, let's break for tea now. And we shall again gather at 11:15. Right, so precisely 11:15. Okay, thank you so much. Let's thank. I am not. Prof said before. He is the boss. It's 7 o'clock.